So welcome to the Non-Destructive Testing and Evaluation course. The course code is ME8097 for the regulation 2017. And in this video session, we'll be studying about the fifth unit of radioactive testing. And here we'll be studying about the radiation sources and the type of radiography. So this is a syllabus of the fifth unit. We'll be studying about the principle of radiography, interaction of X-rays with matters and imaging, film and filmless techniques, types and uses of filters and screens, geometric factors, inverse square law, characteristics of the films like grainness, density, speed, contrast, characteristic curves, and we'll be studying about the types of penetrometers, exposure charts, and the radiographic equivalents and fluoroscopy, zero radiography, computer radiography, computer tomography. So the first is the radiation sources. So commonly two sources of radiations in industrial radiography are X-ray generators and gamma ray sources. And this industrial radiography is often subdivided into X-ray radiography or gamma radiography. So this all depends on the source of radiations used. So the first diagram you have, first figure you have this X-ray examination of aircraft panel in which you have this X-ray tube, and the second one is the gamma ray equipment. So gamma radiography. So this gamma rays are produced by radioactive isotopes. So this radioactive isotopes usually has an unstable nuclei that does not have enough binding energy to hold the nucleus together. So this nucleus would break down spontaneously and resulting in the release of energy and matter is known as radioactive decay. So most of the radioactive material used in industrial radiography is produced artificially, and this can be done by subjecting stable material to a source of neutrons in a special nuclear reactor, and this process is called as activation. So unlike X-rays, which are produced by machine, gamma rays cannot be turned off because radioisotopes used for this gamma radiography are encapsulated to prevent leakage of the material. And here you have this iridium-191 before activation and the encapsulation. So the radioactive capsule is attached to a cable to form what is called as a pigtail. So here it's this diagram shows a pigtail, and this has a special connector, and at the other end that attaches to a drive cable. So here the device called a camera. This is a camera setup is used to store, transport, and expose the pigtail, which we saw in the previous slide, and containing the radioactive material. So the camera contains the shielded material, which will reduce the exposure of radiation during the usage. So here you have a hose-like device called a guide tube, which is connected to the threaded hole called exit port in the camera. This is the camera unit. And the radioactive material will leave and will return to the camera through this opening when performing an exposure. So here a drive cable is connected to the other end of the camera. So this cable controlled by the radiographer is used to force the radioactive material out into the guide tube, and where the gamma rays will pass through the specimen and expose the recording device. So here the radiographer is connecting the drive cable to the pigtail of this camera unit, and here this line diagram shows exposure device. This is a camera unit, actually. This is a source inside, and here you have this drive cable, and this is the crank out which is rotated, like you have this stored position of this camera unit. So X-ray radiography, unlike gamma rays, X-rays are produced by an X-ray generated system. This is an X-ray generated system. These systems include an X-ray tube, head, a high voltage generator, and a control console. So this is what the X-ray tubes as shown here. X-rays are produced by establishing a very high voltage between these two electrodes, that is a cathode and anode. And to prevent arcing, the anode and cathode are located inside a vacuum tube. So this is a vacuum tube which is protected by a metal housing. And here this cathode contains a small filament, such as the same as in light bulb. So current is passed through the filament. Which heats it, and this heat causes electrons to be stripped off. So the high voltage causes the free electrons to be pulled towards the target material. This target material usually made of tungsten, which is located in the anode, and this electrons is made to impact against the target. So this impact causes an energy exchange, which causes X-rays to be created, and these X-rays are made to fall on the test specimen. So you have several different imaging methods. So film radiography, real-time radiography, computer tomography, and digital radiography, and computed radiography. So these are all the imaging modalities. So coming to the film radiography. So it is one of the most widely used and the oldest imaging mediums in industrial radiography, is using this radiographic film. And this film contains a microscopic material called silver bromide. And once exposed to radiation and developed in a dark room, the silver bromide will turn into black metallic silver, and thus the image is formed here. So here the film must be protected from this visible light. Just like the X-rays and gamma rays can expose film. So film is loaded in a light-proof cassette. So this is a cassette. And this cassette is then placed on the specimen. So here you can see the film is placed on the specimen. So opposite the source of radiation. And this film is normally placed between the screens. You have intensifying screens, and this film is placed in between the screens to intensify radiation. And in order to view the image, the film must be developed in a dark room. So you need to develop the film in the dark room, and this process is somewhat similar to the normal photographic film development. And this film processing can either be done manually or in an open tank or in an automatic processor. So these are all the diagrams, figures which shows the processing of the film. So once a film is developed, the film is referred to as a radiograph. So after the film is developed, and this developed film is called as a radiograph. So here you can find out the defects in this component. It has been marked, and this is actually the electrical fuse manufactured with wire element, which has been recorded in the film. So coming to the advantages of radiography, and it is limited by material type or density, and it can inspect assembled components. Minimum surface preparation is required, and it is very sensitive to changes in thickness, corrosions, cracks, and material density changes. And it can detect surface and subsurface defects, and you can provide a permanent record of the inspection. Disadvantages. Coming to the disadvantages, you have many safety precautions. Many safety precautions is required for this, and many hours of technician training is required prior to use. So need to assess both the sides of the sample. So orientation of equipments and flaws can be very critical, and flaw depth is impossible to determine without additional angle exposures, and expensive initial equipment cost. So coming to the applications of radiography testing, it's used to inspect most types of solid materials, both ferrous and non-ferrous alloys, as well non-metallic materials and composites, and inspect the condition and proper placement of the components for the liquid level measurement of sealed components. It is used to test the castings, weldments, and forgings when they are in the critical need, and to ensure the objects is free from internal flaws. So semiconductor devices for detection of cracks, broken wires, unsoldered connections, and foreign materials and misplaced components, whereas other methods are limited in ability to inspect semiconductor devices. You can go for this radiography testing. So with this, we come to an end to this video section. So thank you and have